Hello everyone, we are Kihu
And I'm Jintai Lee.
today we will walk you through our approach to building a medical insurance cost prediction model for the M3 practice hackathon. In this discussion, we will cover the models we selected and the reasoning behind our choices, the steps we took to improve performance through feature engineering and parameter tuning, how we assess the fit of our requester using learning curves and validation techniques, and our final results along with possible future improvements. To begin with, we started with a few simple regression models, including linear regression, ridge regression, and lasso regression. These models provide strong interpretability, but we found that they lack the ability to capture complex patterns in the data. As a result, we decided to enhance our approach by incorporating ensemble models. We added three additional regressors: random forest regressor, gradient boosting regressor, and XGBoost regressor. Random forest is a bagging method that builds multiple decision trees and averages their outputs to reduce variance. Gradient boosting is a boosting method that improves predictive power by sequentially correcting errors made by previous models. And XGBoost is a optimized gradient boosting algorithm known for its speed and efficiency, making it a strong candidate for improving our performance. We also decided to remove support vector regression, the SVR, from our models as it performed poorly during preliminary tests. Given the nature of our dataset, tree-based models were a better choice due to their ability to handle structured tabular data more effectively. To maximize the accuracy of our predictions and minimize mean square error, we implemented several performance enhancing techniques. First, we performed feature engineering to better prepare the data for machine learning models. Categorical variables such as sex, smoker, and region were converted using one-hot encoding to ensure they were properly interpreted by the models. Numerical variables like age, BMI, and children were standardized to prevent scale differences from affecting model performance. Additionally, we introduced new interaction features such as the relationship between BMI and smoking status, as smoking amplifies health risks and could significantly impact medical insurance costs. Hyperparameter tuning played a crucial role in optimizing our models. We use both grid search CV and randomized search CV to systematically adjust hyperparameters and find the best performing configurations. For random forest, we optimized parameters like the number of trees, maximum depths, and minimum samples per split to balance complexity and generalization. For XGBoost, we fine-tune learning rate, number of estimators, and tree dips to prevent overfitting while maintaining strong predictive performance. These optimizations help us refine our models and improve their overall accuracy.
And to ensure that our models were well fitted and not overfitting to the training data, we used multiple validation techniques. And one of the key approaches was k-fold cross validation, where we divided the data set into multiple training and validation subset to obtain a more reliable measure of model performance. And in addition, we plotted learning curves to visualize how the model's error evolved as more data was introduced. And if training error was significantly lower than validation error, it suggested overfitting, whereas high errors in both training and validation would indicate underfitting. And our learning curves helped us to determine that our initial models had slight overfitting issues, which we addressed through hyperparameter tuning and regularization techniques. And another method we used to assess fit was residual analysis. By plotting residues, we checked for systematic patterns that might indicate bias in our model. And ideally, residues should be randomly distributed around zero. suggesting that the model is making accurate predictions without systematic errors. And after evaluating all models, we found that XGBoost achieved the lowest RMSE and the highest R square score, and making it the best performing model for our data set. And once we finalized the model, we created a submission file and uploaded to Kaggle to access our ranking on the leaderboard. And we iterate on our model by refining hyperparameters and testing different features, um, engineering approaches, and submitted multiple versions to optimize our position in the competition. And given more time, we would explore additional methods such as stacking, which combines multiple models to create a meta learner that further refines predictions. In summary, our approach to this hackathon involved careful model selection, feature engineering, hyperparameter tuning, and rigorous validation techniques. And by leveraging ensemble models like random forest and XGBoost, we were able to achieve strong predictive accuracy while ensuring that our model was well fitted and generalizable. And if we were to extend this work, we would consider incorporating deep learning models using um, SHAP values to improve interpretability and refining feature selection strategies. And this has been a value learning experience, and we appreciate the opportunity to apply practical machine learning techniques in a competitive setting. And thank you for watching our discussion, and we wish everyone the best.